today is, what's the best way to explain this? A lot of it's just kind of by feel. You have to know some vocabulary and you just sort of have to understand it. There's not a lot of work to do, really. I got to sneeze. I go, oh, goodness. Excuse me. Okay. So we've been talking about polynomials this whole chapter. We've been factoring them. We've been solving them. We figured out how to find the zeros. The last half of the chapter, basically, we're going to learn how to graph them. So we just need to learn to talk about them in a proper mathematical way. All right. So first thing, every single polynomial that you have, which we learned at the very first section what a polynomial was. It's just something where you've got, like 3x to the 7th minus 9x cubed plus 2x squared plus 4. That's a polynomial where you've just got the single variable. All the variables are raised to a whole number. You're never going to have any negative exponents. You're never going to have any fractional exponents. There's no, variables get multiplied by other variables. It's the sum of them, and you have these coefficients out front. Like on here, the degree of this is 7 because it's the highest power. We've written it in standard form, which is descending order. The leading coefficient is 3. The constant term is 4. These are polynomials. They are both smooth and continuous, no matter how you draw. Like every single polynomial function, when you draw it, will be smooth and it will be continuous. Now this is just kind of a, sort of a layman's definition, but smooth just means there's not going to be any sort of like sharp points or gaps in it. Well, actually, I probably shouldn't say gaps. That's more continuous. But like smooth, it's just a nice smooth curve. You're not going to have anything where it comes to a corner type deal. Okay. The continuous part, there's not going to be any gaps. So it's not going to pick up and jump someplace else. It's not going to have any holes in it. So this would be an example of a polynomial function. This would not, because it has both holes, gaps, and they call those all the time cusps. Some people call them sharp points. It's just all depending on who you ask. Anyway, so every single polynomial function is smooth and continuous, which may not seem like a big deal right now, but when you get to calculus, it'll be a huge deal. So know that going in, okay? Also, let's just talk about some of the words we can use when we're describing polynomials. Let's pick something. Well, first, you describe a polynomial usually based on the x value. So like say we say this is x value A, let's put right here's B, right here's C, right there we'll call that D, here's E, right there let's call it F, and G. Okay, so like those are all the important x's. So we've been talking about x-intercepts. X-intercepts, it would cross or touch the x-axis at A, C, E, and G. Okay, it crosses at those. It touches at this one. Later on in the chapter, we'll figure out how to tell based on the equation which of those it does. It'll all make sense as we go. But that's all what's happening. We can talk about these points right here. See how, well, actually, before I do that, I should talk about something we already have discussed, increasing and decreasing. So here, I'll get a highlighter out. When you read it left to right, increasing function, increasing function, increasing function. So all those yellow spots where this is an increasing function. So you would say as you read across it, we're going to be increasing from negative infinity up to B. Then we're increasing from D to E, and then we're increasing from F to infinity because you describe it by the x values where it happens. Okay. Decreasing, reading left to right, that's where it's heading down. So we're decreasing here. We're decreasing right there. And then those points where you swap over from increasing to decreasing, whichever way, we call those relative extrema. They can be a minimum or a maximum. So, and the thing you're going to do for homework calls them a relative minimum, a relative maximum. Some people call them local minimums and local maximums. I actually kind of like the word local better, but Delta Math didn't ask me. So right here, like say it when X is B, you're swapping from increasing to decreasing. So right there at B, this thing tops out. That's called a local or relative maximum. The reason why it's got the word relative or local is not because there's a difference between an absolute maximum value versus a relative maximum value. So like in this one little localized area, that's where it tops out. But it's not the highest it ever gets. Like all this stuff over here is higher. And if we were going to use the word absolute maximum, we couldn't here because it just keeps going up. There's not a place where it's just as high as it's ever going to be. But like in that one area, there's where it tops out. So when X is B, we have a local maximum value of whatever height that is. Like right here, when X is D, we have a local minimum value or a relative minimum value. Right here, where X is E, we have a local maximum. Right here, where X is F, we have a local minimum or a relative minimum. Okay. We can also describe a graph by whether the values are positive or negative. And that's different than increasing and decreasing. Okay. So like if you're looking at this graph, anytime because the value of a function is its y value. That's the output. So anytime you're above the x-axis, the function has a positive value. Anytime you're below the x-axis, the function has a negative value. Anytime you're on the x-axis, the function has a value of 0. The zeros of a function, we already talked about that. Zeros of a function are the x values that create an output of 0. So the zeros of this function would be A, C, E, and G. Okay, so that's just a whole bunch of vocabulary. Here's some things that we've kind of discussed already that we kind of just throw at you today. We've talked about x-intercepts all through algebra. Like we did x-intercepts in algebra 1. We're doing them right now. You let y be 0 and you get an x-intercept. We also call those zeros of a function. So, if you're looking at whatever r is to make the function equal 0, that value of r is called a real 0. Okay. So the r, whatever it is a 0. R is also an x-intercept. Intercept, when you graph it, x minus r is a factor, and then r is a solution to what x is. So let's say you just had this function right here, 3x minus 9. If I asked you what's the 0, you'd be figuring up what makes 3x minus 9 equal 0. And it'd be 3. Because f of 3 would equal 0. Okay? If they said, what's an x-intercept? Then you would just say it's 3. Or you could list it as a point. X minus 3 would be a factor, because I could factor the 3 out and leave x minus 3. And then the solution, or people will call them roots, is if you set this equal to 0 and you told me the x value that makes it true. All the same stuff, just different ways of saying it. All right, so I think this example right here may help you understand maybe a few of the things you've been doing wrong. Find a polynomial function of degree 3 with a lead coefficient of 1 whose zeros are -3, 2, and 5. Okay, so let's say we've got a function. If a 0 is -3, that means one of the factors is x plus 3. If a 0 is 2, it means one of the factors is x minus 2. If a 0 is 5, that means one of the factors is x minus 5. So if we wanted to multiply this out, we're going to get, let's see, x squared minus 2x plus 3x. That's a plus x. Oops. Minus 6. And we'll keep distributing. Let's distribute the x squared. Distribute the x. Distribute the negative 6. So the polynomial function x cubed minus 4x squared minus 11x plus 30 has a lead coefficient of 1. Yep. Make that go away. A degree of 3. Yep. And just check. Like if I were to plug it, let's do it the new way we figured out. If I were to plug a 2 in, according to the remainder theorem, yep, it does equal 0. The same thing would happen if I plugged in a negative 3 or a 5. All right. I just think it's kind of helpful sometimes. Like we've been starting here and figuring those out. Sometimes I think it's helpful to see what the answers were and see how the function is created. All right, now this one's kind of tricky. It says, find a polynomial function of degree 5 with a lead coefficient of 1. Whose roots are these? Or whose zeros are those? Well, this all still has to be true. But that, if you multiply that out, you're only going to have x cubed. That's a degree 3. How in the world can you throw in another x squared without having a 0? Okay, did you notice up here? It's a real 0. Like if I want to have this set equal to 0, yeah, there's all sorts of things that solve it. But when it comes to graphing them, you can't graph imaginary numbers on a regular old coordinate plane. So it's like, and also, did you notice how it said a polynomial function? It didn't say the polynomial function. What if I just made up a factor that would give me no real zeros? Like the way I know that is if I took and set that equal to 0. Yeah. I can't graph those. Oh, actually, I really should have put that. Ugh, I messed up the notes. I've already run the copies. Add in the word real right there because the word real should be there. Okay. All right. So like I said, we're working our way up to being able to graph them. Today, we're just getting terminology, thinking about how the functions are made. Now we're going to talk about something called end behavior. So here's just some graphs. And you're just looking the way you say this right here, as x approaches infinity. So as your x's get bigger and bigger and bigger, what do your y's do? Oh, they get bigger and bigger and bigger. As x approaches infinity, f of x also approaches positive infinity. As x approaches negative infinity, what do your y's do? Oh, they approach positive infinity. As x approaches positive infinity, your y's approach negative infinity. As x approaches negative infinity, your y's approach negative infinity. As x approaches positive infinity, your y's, f of x's, approach positive infinity. As x approaches negative infinity, your y's approach negative infinity. Like this is called the end behavior. What happens out on the ends? Okay, so let's just try one. I'm going to keep that graph where you can't see it. Just don't look at it. Here's a function. It's next to the fin. As x gets bigger and bigger and bigger. Okay, here's the best way I can tell you how to think about this. Like if x were 2, these x's right here make a big old difference. Big difference. Okay? But if x turns into 2,000, that is so much bigger than all of this. It's not that it still doesn't make a difference. It does. It's always going to make a difference. But The bigger X gets, the less of a difference it makes. It's kind of like if you're talking about how much money you make. Okay. If you've got a part-time job and you're making $10 an hour and somebody gave you $1 an hour raise, that's a huge deal for you. If Elon Musk got $1 an hour raise, he wouldn't even notice because as the numbers get bigger and bigger and bigger, a small change makes less and less difference. Okay? So the way you figure out what happens out on the ends, because when you're going out on the ends, that's when you're heading towards infinity and negative infinity. Like you're getting huge numbers, absolute value-wise speaking, is that you focus in on the dominant term. And the dominant term is the one with the biggest power. You just kind of let all this disappear because those matter when you have small x's. And again, they still matter. They make a difference on what the outcome is, but they make less and less the longer you go. So it's like, okay, what would happen if I plugged in bigger and bigger positive numbers right here? Oh, I'd get bigger and bigger positive numbers. So as x approaches positive infinity, f of x will also approach positive infinity. But if I let x approach negative infinity, and I'm worried about what's happening with that dominant term because it's gonna take over. It's like the bully of the polynomial. It's gonna dictate what happens to everybody else. If you take a negative to an odd power, you get a negative number. But absolute value-wise, it's huge because you're taking it to the fifth, and then you times by 3, it gets even huger, but it has a negative on it. So as x approaches negative infinity, f of x will approach negative infinity. And then just to let you see, on Desmos, here's what it actually looks like. Like when you're in here close to 0, they make a big difference, but it just started shooting off each end. And so here's the thing from the book. It says if the degree is odd, so think about, I got x to the 7th, blah, 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 blah. And the lead coefficient is positive. As you're heading towards positive infinity, positive numbers to the 7th power are going to be positive numbers, but the bigger x gets, the huger those get. As you go off towards negative infinity, negatives to the 7th power, that's an odd power, those are going to stay negative, but the absolute value-wise, they're going to be huge. You're going to approach negative infinity. Okay? If you put a negative, say it's like negative x to the 9th plus blah, 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 who cares? Okay? So if you head off towards positive infinity, right here, you take big old positive numbers. Why will it not? Right. Take big old positive numbers, raise them to the 9th. They're huge positive numbers, but they don't want the opposite. So they're going to head down. And then you head towards negative infinity. You take negative numbers, raise them to an odd power. They're going to be negative, but when you do the opposite, they're going to be positive. And you've got these giant numbers raised to these big old giant powers. They're going to be huge. Okay? So when you have an odd degree term, you do different things on each end. However, when you do an even degree term, say it's like x to the 6th plus blah, 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 blah. Heading off toward positive infinity, it's going to get bigger. You take negative numbers to the 6th, you're going to get positive numbers. And then as they head towards negative infinity, absolute value-wise, those numbers are huge. Raise them to the 6th power, they're going to be even huger. Okay, so if you see on a graph, and then the same thing goes, if you have the even, say it's like the opposite of x to the 8th, blah, 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 because that's your dominant term. Same exact stuff goes there. So if the two ends do the same thing, it's got to be an even-powered polynomial. If they do opposite things, it's got to be an odd-powered polynomial. And your assignment tonight, or over the weekend, is going to be some delta math stuff. So they're sitting there. These are the two that the other honors algebra 2 classes are going to worry with the most. So that's the ones you have the most questions on. But these are just, they're just so important that you have that terminology down that I just want to make sure you go through it. So hopefully that homework will it'll go pretty quickly. If you've noticed, I still hadn't put that delta math stuff in because I just hadn't sat down and sifted through it because I've just been dreading it because there were so many of them, but I got to look for the ones that are capitalized. It's going to just take me a day. So if you haven't finished all that, I haven't looked at them yet. You can feel free to finish that this weekend while you're logged in.